We last time talked about multi-particle systems and energy and angular momentum, and looked at a 1D example looking at a two-particle system. Right now, we'll look at a two-particle 2D example system. So here we go. I mean, I don't know what you call aliens from Venus. Venusians? I think Venetians? Venetian sounds like you're from Venice, like Venetian blinds. So I don't know. All right, so this is it's a contrived example, but it helps, you know, get ideas across. We're basically just taking the same two-particle situation, two particles connected by a spring. All right, M1, M2, and they're free to move in the 2D plane. So there's no gravity. It's just this kind of 2D world. If you want, you got two hockey pucks on ice connected by a spring, and you know, ignore friction. How do these things move? And maybe you have some intuition. So this spring, it only acts along the line between the two. So in general, the motion will probably look like this thing kind of moving in a straight line and then this thing oscillating back and forth. But then if it had some initial rotation, it could do something else. So can we figure that out? Well, the only forces are going to be due to the spring. Are due to the spring. And so these are internal forces in our categorization of external versus internal. Right, so there's going to be the force on particle 1 due to particle 2, and vice versa. So no external forces. So because there's no external forces, that implies that the acceleration of the center of mass with respect to some inertial origin, could be some arbitrary origin out here. And where's the center of mass? It's going to be somewhere along the line connecting the two. Oops, there we go. This inertial acceleration is 0. So this thing moves at a constant speed. It's some kind of constant velocity vector, which means the motion of the center of mass is boring. Nothing interesting there. So we can jump onto the center of mass centered frame. So let's just do that. Here's our center of mass. It's on the line connecting M1 and M2. And we'll write this as E1, E2. All right. This system would could be written in terms of polar coordinates, right? If we write the location of each particle with respect to the center of mass, so here is, let's call this R2 with respect to G, and then we've got R1 with respect to G. We can look in this G-centered frame. And use the center of mass corollary. As referred to by the book. The center of mass corollary means that M1 R1G plus M2 R2G equals 0. Okay. To simplify things, let's just assume that these are equal masses. Okay, so the center of mass is exactly in the middle between the two. So if M1 equals M2, these masses will cancel out and we'll get that R1G equals negative R2G. So this is just like a vector version of what we had last time in the 1D case. We can use polar coordinates to describe, we can pick one of these. Let's pick mass M2, the location of mass M2. So that means polar coordinates, R and theta. So we'll use, like this is R, and then this angle is theta. Okay. If we use polar coordinates, that means that R2G equals R in the ER direction. So let's define this frame. Maybe I'll use orange here. Here's the ER direction. Here's the E theta direction. Polar coordinates again, and we know everything about polar coordinates, hopefully by now. So if R2G equals R in the ER direction, then because of this center of mass corollary, this tells us that R1G is negative R ER. What else can we do? Well, we could write the force. This is a spring. Let me say something about this spring. The spring has a spring constant K and an equilibrium length, we'll say L naught, just like we did for the 1D example, okay? K and L naught. So we could write down the force directed along that ER direction, right? F12, the force on particle 1 due to 2 and the force on particle 2 due to 1. But we talked about potential energy last time. So we're going to write the spring force, or the force due to the spring, in terms of potential energy. And why can we do this? The force due to the spring is a conservative force, so we can write it as coming from potential energy. And things related to elasticity in general come from a potential energy. Gravitation come from a potential energy. Later we might talk about some other forces that come from potential energy, but here we're just talking about the spring force. So here we used capital U. Maybe we'll write capital U sub spring. It's the force due to the spring. And this is 1/2 K, right? The energy due to a spring is 1/2 the stiffness and then the stretch in the spring squared, which for now we'll say this, the distance between the two masses is L. So L minus L naught is the stretch in the spring, and that is squared. So this is 1/2, and what is L? L is, given what we've written in terms of R, this is 2R. So this is 2R, and then we'll just define, where should I do it? All right, 2R naught. R naught is, we'll just define it as L naught over 2. Okay, it's just half the spring equilibrium length. So then we've got that. Multiplying through, what do we get for U? This ends up being 2K R minus R naught squared. Okay, so that's our potential energy. The kinetic energy, so here's potential energy. What about kinetic energy? Kinetic energy, use the symbol T, and here it's just kinetic energy with respect to our chosen origin, which is the center of mass. So we're not considering the kinetic energy the part due to translation of the center of mass. We're in the center of mass frame, so it's just kinetic energy of kind of the relative motion. So this will be T1g plus T2g. All right, and what is T1g? It's just 1/2 the mass inertial velocity of 1 with respect to g squared. But that's going to be exactly the same as T2g, which is 1/2 m inertial velocity of 2 with respect to g squared. We've done polar coordinates enough that hopefully you know what this is going to be. This is going to be r dot squared plus r squared theta dot squared. So the total kinetic energy is twice that. So twice 1/2 means we're just left with m r dot squared plus r squared theta dot squared. So there's our kinetic energy. Why are we doing this? We're not actually going to solve Newton's laws to find out what the motion is. We're going to use conservation of quantities like energy and angular momentum. So we've written these two energies. The only forces that do work are conservative forces, so total energy is conserved. That means it's constant during the motion. And what is that total energy? We could write it as E sub g. It's Tg plus U. And we could just write it out. So this is an expression in terms of the polar coordinates and their time derivatives and some constant parameters like m and k and r naught. That's our total energy, and this thing should be a constant, meaning you give it initial conditions, the energy, even though kinetic and potential energy could be fluctuating, the total energy will stay the same. And we'll use that at some point. But now we're going to use another fact that results from that there's no external forces, right? There's no external forces, so not only do we have that the acceleration of the center of mass is 0, the total moment due to external forces is 0. And if you recall from our discussion of the total angular momentum, if the total moment is 0, then that means total angular momentum is a constant of motion. So let me just write that again. Since there's no external forces, that implies no external moment, which has a symbol, this is MEXT, and we're talking about the center of mass. So there's no external moments, so total angular momentum is also conserved. All right. And I guess we need to specify the total angular momentum about the center of mass. So now we need to write what the total angular momentum is. To get that, we need to write the individual angular momenta of each particle. So the angular momentum of particle 2 about the center of mass, it's going to end up being the same as particle 1 about the center of mass. And it'll be, this would be like m, the location of particle 2, cross the inertial velocity of particle 2. And it's going to be, since R2g is negative R1g, that's why these two things are the same. And if you work out what that cross product is, we've already done the cross products for polar coordinates, so I'm not going to repeat it. So this is the mass r squared theta dot in the E, I guess we'll call it the E3 direction. That's just the third direction coming out of the screen. Okay. So the total angular momentum with respect to the center of mass is the sum of these two. And that is 2 mr squared theta dot E3. All right. And in general, the equation of motion for this total angular, well, that's nice. The time rate of change of the total angular momentum would be equal to the moment due to external forces. And this is 0. So that means this is a constant. It's a constant vector. So this thing is equal to a constant, meaning whatever we have for the initial conditions of r and theta dot, even though r and theta dot could fluctuate in time later, this product of the two must be constant. What do I mean? I mean, if you've got from initial conditions lead to our initial, that's just a h sub 0, it's just some value, 2m, the initial r squared, and then the initial theta dot. We have that 2m r squared. Let me put in explicitly the time. I think that helps. At some later time, theta dot at some later time has to equal this constant value. Okay. Now we can use these conservation laws. Let's go here, this energy one, let's call this equation 1. That's a conservation law. And then this is equation 2. It's another conservation law. And we can use these two. One and two. Let's just put it as to learn some things about the motion, totally skipping Newton's laws. Skipping Newton's laws. Or I guess we're talking about mostly Newton's second law, the one that's the law of motion. If you, and I'm not going to go through the details. This is, in essence, what you are expected to do for homework problem 2. For the situation of the two masses and they're connected through a hole, you can go through the same kind of exercise because it should conserve energy and conserve total angular momentum. So you can use these two laws, plug one into the other. I think it's that you'll plug this formula 2, use this relationship in the energy relationship, formula 1, and you get an equation. There'll be some algebra, but you'll get an equation of the form r dot squared equals some function of r and parameters. How is that? We can use this, and I actually wrote this wrong. This is theta at some given time. You'll use equation 2 to basically rewrite theta dot over here in terms of r and initial conditions. And then you'll be left with something like this. So this right-hand side has parameters. Parameters are things like k, m, r naught, and initial conditions. It might not be the prettiest looking function of r, but it'll be there. Okay, so what does this mean? dr dt squared equals f of r, which we could split into two cases. There's dr dt equals, this should be a bracket like that, hr for r dot greater than or equal to 0, negative hr for r dot less than 0, where hr is square root of fr. Now it's useful to have a picture to kind of interpret what we're doing here. We could plot r versus r dot. This is called a phase plane. It's the r and r dot phase plane. But we'll have, say, if we start with r dot equal to 0, so here's our initial time, t equals 0. We start at some initial r value. Then this thing, the way that the r dynamics evolves, the radial dynamics, remember the radial dynamics is just the distance between the two particles. It's half the distance between the two particles. We'll have this happening. What is this? This is just HR. So we're plotting HR, right, versus R. And we get this upper half of a cycle. So that's this part. And then the second half of a cycle, it's mirror image, it's negative, and should look nicer than that. This is negative HR. And what we've got these two, I've used the term turning points last time. So these are turning points. This is the minimum R, and then this is the maximum R. So the motion will go between a minimum separation between the two particles and a maximum separation. So we're just looking at that radial dynamics. So this forms a cycle. Let's say this thing starts at t equals 0. When it comes back here, it's gone a full cycle. Let's call that t equals tau. So motion in R is a cycle. It's periodic with a period tau. After you go a half cycle, well, that's t is tau over 2. And then this cycle just keep repeating. That's it. The radial motion is just a repeating thing. It might not be exactly a sine curve, but it will be periodic. So let's consider just the motion from the initial condition to half the cycle, t equals tau over 2. So just this red curve. for that, dr dt equals hr. So that's our equation of motion for r. What can we do with this? We can do separation of variables and get, we'll get dt by itself. And then on the other side, we'll have dr over hr. We could integrate both sides. In time, this goes from 0 to tau over 2. And in the radial limits of integration are from r min to r max. And what are those? R min and R max are where HR goes to 0. You could integrate both sides, right? This will give you tau over 2, so half the cycle. And then this will give you something. If we'd like a little sketch, what we're integrating is there's going to be the same limits, R min and R max. This is R. And then we'll plot 1 over HR. So this curve is 1 over HR. It's going to go to infinity at R min and R max. And this, the area given by this integral is the area under the curve between R min and R max. And this is something that you could do numerically. So this is the area under the curve here. So you can numerically do that, and if we knew what the initial conditions were, we would get some number here. Okay, so you would use this same procedure to solve for the period of the radial motion for homework 2.2. I think it's part B. And here's a little gift. I'll give you the answer. What you should get. You should get that tau, remember you're solving for tau over 2. So whatever you get for the area under the curve multiplied by 2. You should get tau is about 1.34 seconds for homework problem 2. Okay. So that's, in some sense, by using both conservation laws, we've turned the equation of motion for the radial dynamics into just this first order ODE that is then much easier to deal with. In fact, you can analytically get an example without solving Newton's laws. You will, I think, have to numerically approximate this integral. So you can numerically get the integral, because HR is kind of a pain. All right. Just like last time, we could talk about the energy perspective. I guess before I do that, once we know the R dynamics, if we knew how R changed in time, then from this equation up here, the conservation of angular momentum, if we know how R changes, then we could find out how theta changes. But the motion is going to look like, I'll show you what the motion kind of looks like. It looks like in the center of mass frame, it's going to look something like that. So you've got both rotation and the expansion and contraction of the spring. And just like an ice skater bringing in their arms, spins faster. This thing is spinning slightly faster when the masses are closer together. I don't know if that shows up good in this video, but that's the type of motion going on. Okay. So what's the energy perspective? We'll just, let me just rewrite. I'm just going to rewrite the energy from above since it's off the screen. mr dot squared plus r squared theta dot squared plus 2k r minus r naught squared. All right. I'm going to do something else over here on the right side of the screen. From the conservation of angular momentum, we had 2m r squared theta dot equals whatever the initial angular momentum was from initial conditions. We can rewrite this, theta dot equals h naught over 2m, just put the parameters separately, 1 over r squared. Okay. And I'm going to rewrite this as h naught over m r 1 over r squared, where m bar is defined to be 2m. And I'm going to define something called k bar, which is 4k. So over here, this we could rewrite the energy in terms of just r and r dot, because we could rewrite theta dot using this formula, actually use this formula to kind of eliminate theta dot. Okay. So what will this end up being? This ends up looking like m bar over 2 r dot squared plus r squared. And now we have to do theta dot squared using this formula over here on the right. H naught squared over m bar squared, 1 over r to the 4th plus 1/2 k bar r minus r naught squared. You notice we've got this 1 over r to the 4th and then this r squared here. So some things cancel out. We've got what? R dot squared plus, I like to put parameters in front, so h naught squared over m bar squared, 1 over r squared plus 1/2 k bar r minus r naught squared. We could rearrange things further so that this looks like this is 1/2 m bar r dot squared. It's the only thing that seems to have a velocity in it. If the catches up, there we go. We'll call this an effective kinetic energy, T effective, plus h naught squared, 2m bar, 1 over r squared, plus 1/2 k bar r minus r naught squared. This thing over here I know is the potential energy due to the spring, but I have something here that it doesn't have a velocity in it, so it's not a kinetic energy. We'll call this just an effective potential energy. And we know that whatever this is, it's the total energy, remember, this is constant during the motion. So the energy perspective, I like to give little graphs of the energy. It helps me think about stuff. So the variable here is r, and the vertical axis will just plot energy. we've got the we've got two different potential energies. So let me look at the effective potential energy. The effective potential energy, its dependence on R is this 1 over R squared. So this is going to look like it's going to go to infinity at R equals 0, and then it's going to kind of go to 0 at large R. So this is the effective potential energy, and I'll use this symbol that means proportional to. Looks kind of like an elongated alpha, but it's proportional to 1 over R squared. Okay, then there's the spring. The potential energy due to the spring is going to be a parabola that goes to 0 at R naught, and it's opening upward. So here's the spring. This is proportional to R minus R naught squared. So it's a parabola. You add up those two potential energies, and that gives you the total potential energy. So add these two up, and you'll get something. I don't know, we'll draw it that way. What's this curve? This is the, we'll call this U total. And it's U of the effective potential plus U of the spring. And then based on our initial condition, we'll have a total energy, which is just this, we draw it across as a straight line. This is EG, total energy. It's going to be constant, which means it's also flat as a function of R. What are we left with? The distance between the red curve and the blue curve, so the total energy and the kinetic energy, right? Because we could write T effective equals EG minus U total. Maybe I could do EG in red just for fun. Okay, so we've got that expression. So the distance between the red and the blue curve is the effective kinetic energy, which is also, 1/2 m bar R dot squared. So it looks like we have, even though this is a 2-particle system, the dynamics looks like, at least in the radial direction, it looks like we have effectively 1 particle of mass 2m, or m bar, and it's experiencing a potential energy due to the spring and this effective potential energy that really has to do with conservation of angular momentum. And there are turning points, which I think I plotted those in green. That's where the effective potential energy goes to 0. So where this, it's going to be where the green, the blue curve and the red curve meet. And then that just gives us our limits of the motion, R min and R max. So that's the energy perspective. And we could just right below this, got R and R dot. If I just sort of extend the location of the min and the max, these are the turning points. Term we used last time, turning points of the radial motion. And we could just sketch what if these are turning points, our R dot has to go to 0 there, because the effective potential energy goes to 0 there. And then it'll reach a maximum, like right in the middle. And it'll vary in what a way that looks like a kind of something we sketched above. So, and then there'll be kind of negative going back that way. So this is supposed to be the same curve as I plotted up above. But in terms of the energy perspective, okay. And I don't know if I've used this term before, but R dot, we're writing, this is the R dot phase plane. It's just 2 dimensions of the 4-dimensional phase space, which you could view as R dot, theta dot. We're not going to do anything more, phase planes and phase portraits right now, but that was just the energy perspective on this system. Are there questions about this before we go on? I think as you work through homework problem 2, you'll understand more of this better. But let's just leave that. Okay. All right. Another thing I wanted to get to today is sort of introducing the idea of rigid bodies, but we've been talking in the context of a multi-particle system. So this is a rigid body of particles. So this is a multi-particle system where we assume rigid interconnections between particles. I don't know if any of you have played with Tinker Toys. Tinker Toys were a thing when I was a kid. But I've got a nice picture of Tinker Toys. There it is. So right, Tinker Toys have these, these kind of wooden-looking circle things. Think of those as the particles. And if you you connect things with sticks. So this is like you rigidly attach all these things, and you've got kind of a rigid body of particles. In our idealization, the sticks have no mass. So it's as if we have some particles, like here's particle I, everyone's favorite particle. And then we got other particles. And instead of letting these things evolve freely, we say that there's a rigid interconnection between any 2 particles. So here's particle J. So the line between those 2 is fixed. So this would be R-I-J. Is that right? R-I-J. We say that the magnitude of that is a constant for all I and J. So for every pair of particles. So they're all just rigidly interconnected. It's like we've just got them rigidly attached. Okay. So it looks like a crystal structure or something, or Tinker Toys. So if they're rigidly attached, the distance between them isn't changing. The orientation of the vector could, because we could pick up the Tinker Toy and we could move it around. In fact, what could we do? we could translate it in 3 dimensions, and then we could rotate it. It turns out rotations can be described by 3 dimensions, 3 rotation angles, yaw, pitch, and roll. So once you've rigidly connected particles, it's a huge simplification in how you describe the system. Let me first say that, saying that the magnitude of the vector is constant is equivalent to writing that the time derivative of this magnitude is 0. Which is what we end up using. So let me write, what is a rigid body? It is a collection of particles constrained to be motionless with respect to one another. So we might say relative to one another. But their orientation in space can change. And what do I mean? This is a huge simplification. If I had, so for example, if I had a kilogram of steel, steel is mostly iron, right? So here's like a little cube, kilogram of steel. This is about 10 to the 25 atoms. So about 10 to the 25 particles, right? So that means this should be, if I were to treat it just like a multi-particle system, this is about 3 times 10 to the 25 degrees of freedom, which goes way beyond what I ever want to do. Like try simulating that, good luck. So what nature does, nature makes it really easy to deal with steel. And we're thinking of like the rigid case. Don't think of deformations right now, okay? That's what you learn in continuum. We're just saying, everything's rigidly attached. So it's as if nature conspires through rigidity to simplify this system from effectively a zillion degrees of freedom to just 6. And what are these 6 degrees of freedom? It's 3 degrees of freedom for the translational motion. And then 3 degrees of freedom for rotational motion. 3 degrees of freedom for translational motion should make some sense. Suppose I have I'll just sort of sketch my an inertial frame, and then attached to this body, I've got some body frame. Okay, so this is our body frame. B frame is the body fixed frame. Fixed in the body. It's attached to the body. If I want to describe how, let's say this point P on the body moves around, that's just going to be 3 numbers, 3 degrees of freedom, X, Y, and Z, if you want. And then to describe the orientation of this frame, maybe turn your right hand into a coordinate system. I could, it'll end up being 3 rotations or 3 other degrees of freedom that describe the orientation of that frame. And we'll talk, more about that later. This is just rotational motion. And why is that? You could hopefully convince yourself if you had, Tinker Toys or something, if you have things that are rigidly attached, they can't do any other type of relative motion. So this is the rotational motion is the only relative motion allowed when you have rigidity. Allowed. If we had something squishy, like a balloon or a Nerf ball or other things, well, that goes beyond what we talk about here. That's more like a continuum. So in studying continuum, there's more possibilities. Just so that you know, we're only looking at one because we're looking at this limit of rigidity. But in continuum, I think I've got a little schematic. I don't know if some of you are taking the continuum class. Right, if you have a little piece of material, this is just a schematic in 2D, then an arbitrary deformation, that's this thing that I'm showing on the left. I don't know why it's doing this for me. So this is an arbitrary deformation. Arbitrary, say, small deformation, can be decomposed into different things. This first one, don't concern yourself with the simples. This is expansion, and expansion could be negative, meaning shrinking. So you could have expansion plus shear plus rotation. But we're only considering rotation because if you have rigidity, expansion and shear can't happen. I like to show this just because it's this cool picture I found online. Here's a terribly sheared house. I didn't take this photo, but you could easily imagine this somewhere in Montgomery County. Anyway, if you find a house that depicts rotation or expansion, send it to me. All right, so we're only considering rotation. So let's say something about that. We're gonna say some things about this isn't spelled right. Some kinematics of rigid bodies. And when I say rigid bodies, once you attach a frame B to a rigid body, then all you have to worry about is the kinematics of the frame. And that's the same as the kinematics of the rigid body itself. Man, what am I talking about? Do I have a nice picture of it? I do somewhere. Where is it? This one. Okay. Here is it's another figure from the book. So we've got a rigid body, which the book writes as, script B. Script B. So think of that, that's the collection of particles. So to the rigid body, let's write a very fancy looking B. We attach a frame, which I'll call B, little b, kind of normal. And this is just a 2D representation. And this will be, it has some origin. I don't know, maybe it's the center of mass or it's just some convenient point on the body, but it's definitely on the body. So O prime is attached to the body. Fancy B. And then we've got 2 unit vectors that define the body fixed frame. So we attach this frame, which hopefully you can convince yourself at least B1 and B2, those directions, will rotate with respect to an inertial frame, E1 and E2. which will rotate with respect to an inertial frame, which I've got over here as I, and this is, it's got the origin O and then inertial directions E1 and E2. And I guess this is a key thing, key point. The kinematics, that means how you describe the motion. The kinematics of the frame B is the same as, it's the same as that of the body B. So that means we'll just deal with the frame because that's what we've sort of been using, and let's continue to do that. Let's consider a point P on the body, like in the schematic here. So this is another point on the body. This is P. It's displaced a little bit from O prime. Maybe it's displaced a lot. I don't know. And I'm going to write the location of P, R, P, O, right? The location of a point P on the body with respect to the inertial origin is equal to the location of the origin on the body, O prime, with respect to O, plus the location of the point P with respect to O prime. The green vector equals the sum of the two black vectors. All right, now let's take the inertial derivative of this. The inertial derivative, P with respect to O, equals the inertial derivative of O prime with respect to O, plus how this point on the body moves, which is just due to rotation. So this comes from the transport equation. So from the transport equation that we've now used several times, we get this. This is a fundamental rigid body kinematic equation. This thing. And this is in the book, it's equation 8.5. So we've got this part that's due to just the translational motion. And we've mentioned this angular velocity. So there's some, the body has some, I don't know what direction it's pointing. There's some angular velocity vector of the body with respect to the inertial frame. That's instantaneous. This angular velocity vector might change. If that changes, it'll be changing due to moments. And so that will be rigid body dynamics that give rise to that. But instantaneously, the inertial velocity of a point P on the body is the inertial velocity of some reference point on the body, O prime, plus omega cross R. Okay. So this part is, whoa, due to rigidity. Here. This is true. We have a 2D schematic here, but this is true in 2D and 3D. For any 2 points, O prime and P, fixed in the B frame. All right. When we get further into rigid body dynamics, we're going to be looking at how this omega vector, the angular velocity vector, changes. And like I said, it's going to be changing dynamically, which means that it's due to mass, to the mass distribution and forces in the forms of moments. So we're going to have to know how this thing changes with time. So the angular velocity of the B frame with respect to the inertial frame, how does it change in time? We will need a dynamic equation of motion. It's kind of redundant. We'll need an equation of motion for how omega changes. The first step to getting that would be, we look at the rate of change of the angular momentum of the body about its center of mass. And that will eventually give us the rate of change of the angular velocity. All right, this is the change in the angular momentum about the center of mass. And remember last time we said this angular momentum about the center of mass is just relative motion, motion relative to the center of mass. And then this is the change in the angular velocity. And if we know how that changes, then we've described how the body is moving, how the body is rotating. To get to this, we write the angular momentum as something times the angular velocity. So we're assuming we can write this formula. Now what's in here? This ends up being a 3x3 matrix. And so that's what we'll talk about. In fact, maybe I'll just write up here a heading. We're going to talk about the moment of inertia. No, we're talking moment of inertia for a rigid body of particles. And specifically, I'm following section 11.2.2 of the book. That's the 3D version, but this gets introduced in 2D in chapter 9, but I'll say this is in chapters 9 and 11 if you want to read more. Okay, let me get a picture in here. This looks good. All right. There's our rigid body. All right, so if you remember how we wrote the angular momentum from last time, the total angular momentum of a collection of particles is equal to the sum, 1 through n, m(i)(r)(i)(g) cross the inertial velocity. So we're using g as our origin. But now from up above, what did the transport equation give us? The transport equation says that the inertial velocity of a particle I, so think of, here's particle I in this schematic, here's the center of mass G. The inertial velocity of that particle I with respect to the center of mass equals the velocity of particle I with respect to G in the body fixed frame plus the angular velocity of the frame cross RIG. Now, because I is fixed in the frame, it's attached to the frame because we're assuming it's a rigid body of particles. Particle I is not moving with respect to the body fixed frame. So this is 0. So all we have is this part. So we can put, in here, substitute in omega cross RIG, and then we'll have a cross product of a cross product. MIRIG cross I omega B cross RIG. Well, that's kind of annoying. Because up here, I've assumed that we can write HG equals something times omega. Here, it looks like it's kind of mixed up in the middle of a cross product. So how do we deal with this? We want to, I don't know, pull out I omega B so that we've got, oops, my screen froze, so I will have to go away and come back. Yeah, we want to pull out I omega B so that, oops, why is it doing all this crazy stuff? So that this equals something times I omega